In this chapter, we are going to talk about integers. More specifically, we are going to talk about properties of integers that arise from divisibility. When you try to divide one integer by another, and when you get some remainder and some quotient. This is a notion that does not make sense for real numbers. So now we're going to do something very specific to integers, unlike everything else we have done so far. So in the previous chapters, whatever we did, most of those things could easily be done for real numbers. But now we are doing something that's very, very, very specific to integers. So the first, before we start, the two things you should review by yourself is the notion of long division. You should be able to divide one integer by another, and you should know what prime numbers are, what the definition of a prime number is, and when a number is prime and when it is composite. Okay, with that, let's get going. So this video is about modular arithmetic, and modular arithmetic by itself is a huge area of mathematics. It is the beginning of something called abstract algebra. But of course, we won't have time to do all of that very interesting and sophisticated stuff. So we're just going to do very basics, and I'll just tell you some definitions. I hope that in the future you learn more about this subject, because this is a fascinating subject. Okay, so the first thing we're going to start with is division algorithm. This is something you already know. If I give you an integer and I try to divide that integer n by another integer d, then I might always be successful, but I'll get a quotient and a remainder. So I can write the big integer n as n is equal to d times q, where q is the quotient, plus r, where r is the remainder. And the important thing is that the remainder is always less than the thing I'm dividing by. So let me just do an example, it will become clear. So if I try to divide the number 3 by the number 2, then I'll get 3 is 2 times 1 plus 1. I cannot divide 3 completely by 2, I get a remainder. And so here my 1 is the quotient, and 1 is again the remainder. Let's do some bigger numbers. Let's say I have 125 and I try to divide it out by 10. Then I will get 125 is 12 times 10 plus 5. And here 12 is the quotient and 5 is the remainder. Now with negative numbers, this is slightly tricky, and I'll explain why. So the issue with negative integers, firstly, notice that the thing you're dividing by is always positive. So we don't really try to divide by -2. You might as well just divide by 2. Like 3 over -2 is same as -3 over 2. So you can just move the negative sign to 3 instead of 2. That is, you allow n to be a negative number, but you restrict your divisors to only positive numbers. And that's just a convention. There is no deep reason for doing this. It could easily have been the case if we had done math slightly differently. We could have restricted n to be positive and allowed d to be negative. But that's just convention. Okay, with that being said, now n can be negative. But here's the second issue, that we want r to be positive and between 0 and d. 0 is allowed, but d is not allowed. And this messes up the division algorithm slightly for negative numbers. And I'll give you an example. Let's say I try to do n is -3 and d is 2. Then if I try to just naively say that -3 is 2 times -1 plus -1, then this is not okay. Why? Because here I'm saying that my remainder has to be between 0 and 2. And -1 does not lie in that range. 0 inclusive, 2 exclusive. So this is not a valid way of writing quotient and remainder. So how would I do this? You write -3 as 2 times -2, and that's -4 plus 1. So what I did was I had 2 times -1 plus -1. So I took that quotient and I moved it 1 to the left. So I made -1 to -2. That is, I took this and reduced it by 1. And by doing that, that part became more negative, and so I could make the remainder more positive. And then this is -1 plus 2. Or this is just whatever the new remainder is. So just then figure this out separately. Okay, so let me repeat. What I did was I first wrote -3 as 2 times -1 plus -1. That's just, I did the division algorithm for 3, and I multiplied everything by -1. But then the remainder was negative. That's not nice. So I took the quotient and I reduced it by 1. And that made that term more negative. And so I can then fix it by making the remainder positive, and whatever comes out of it is the correct remainder. Let me just do one more quick example. And then my D is 10. Now I know how to do it when it's plus 125 and 10. I do 125 is 12 times 10 plus 5. So let me just do that as it is without fixing. So it's -12 times 10 plus -5. So I just multiplied everything in that equation by -5. Then I'll take whatever the quotient is, in this case -12, and I reduce it by -1. And so I'll get -125 is -13 times 10 minus 130, and then I'll find the remainder. So the remainder then becomes 130 minus 125, which is 5. And so the whole thing then becomes -125 is -13 times 10 plus 5. Now, from these examples, you might get the idea that every time the remainder just flips sign. That's not the case. So let me do an example where the remainder is very different. So let's say 9 is my n, and my d is 7. And then I'll get 9 is 7 times 1 plus 2. But now if I do -9 and I keep the d the same, then the first thing I'll do is -9 is 7 times -1 plus -2. So I multiplied everything by -1. Then I shrink the quotient by 1. So I'll get -9 is 7 times -2 plus, now I need to find the new remainder. And so the new remainder is going to be -9, and 7 times 2 is 14. I move it in the other side, and that is 14 is 5. And so I get -9 is 7 times -2 plus 5. And that is my quotient, and this is my remainder. Okay, that was longer than I expected, but it's fine. So now we are clear about what the remainders and quotients are. So now we come to the notation. This is just notation. The quotient is denoted by n div d, and the remainder is n mod n, and this n mod d. And this is where the name modular arithmetic comes from. It's this mod. So in the above example, when we had 3 is equal to 2 times 1 plus 1, we get 1 is equal to 3 mod 2, and 1 is equal to 3. 1 is equal to 3 div 2, and 1 is equal to 3 mod 2, where the two ones, the first one is the quotient and the second one is the remainder. In the example, when we had -9 is 7 times -2 plus 5, I'll get -2 is equal to 9 div 2, and then 5 is, 9 div 7, and 5 is 9 mod 7. And again, my div is this thing, and my remainder is mod is the remainder. Okay. Now let me just say that the div is not a very common notation. The book uses it, so we'll stick to it. But you are unlikely to find this anywhere else, whereas this is a more common notation. we use mod everywhere. That's where the name modular arithmetic comes from. So it's the basis of the whole branch of mathematics. Part about modular arithmetic. Let d be a positive integer. Let me just do greater than 2. 1. So what is modular arithmetic? Let d be a positive integer. Then I consider the set. This is denoted z and then subscript d. And this is the set 0, 1, 2, all the way up to d minus 1. Now you should think of this as the possible remainders when dividing by d. So when you try to divide n by d, where n is an integer, then the remainder can either be 0 or 1 or 2 up to d minus 1. That's why we only restrict to positive remainders so that this statement makes sense. Okay, then it turns out that we can define addition and multiplication on ZD. And the way we do that is by taking remainders. So for example, let me take D to be 3, in which case ZD is 0, 1, 2. And now I want to define addition. Now you can see the problem is that if I add 2 to itself, I'll get 4, but 4 is no longer in there. But here's how I'll fix it. I'll define 2 plus 2 as 2 plus 2 mod 3. And that will become 4 mod 3. And that is the remainder that is left when you divide 4 by 3. So that becomes 1. So in Z3, 2 plus 2 is 1. In Z3, 2 plus 1 is 2 plus 1 mod 3, which is 3 mod 3. And when you try to divide 3 by 3, the remainder is 0. So 2 plus 1 is 0. And so on and so forth. Similarly, I can try to multiply things. So I get 2 times 2, let's say, is 4. But now I'll do it in mod 3, and then I'll again get 1. So I'm getting 2 times 2 is 1 mod 3. This is how modular arithmetic works. You can add and multiply things within ZD for any positive integer d. Now, you have to be a little careful. Let's do it for d is equal to 2. And then I do z2 is 0, 1. And now if I try to do 1 plus 1, in this, it becomes 1 plus 1 mod 2. That is 2 mod 2. And that is the remainder obtained when you divide 2 by 2, which is 0. So in modular arithmetic, when you do z2, 1 plus 1 is 0. Now we had encountered this before in a different variant, and that was for Boolean algebra. And you could also define an addition and multiplication there using in Boolean algebra, but that is different from this modular arithmetic. So in Boolean algebra, 1 plus 1 is 1. So note that Boolean algebra is not modular arithmetic. Okay, so be careful when you encounter the set 0, 1 and you're doing addition or multiplication. You could either do it using Boolean algebra or you could do it using modular arithmetic. And it depends on what you're interested in. So let's just do quick one more example. So if I take d is equal to 5, now let me do actually d is equal to 4. Then I'll get zd is 0, 1, 2, 3. And then if I try to do 3 times 3 in zd, that is 3 times 3 mod 4. That is 9 mod 4. And when you try to divide 9 by 4, you get the remainder 1. 3 times 3 is 1 mod 4. And in fact, this means that 3 inverse is 3 mod 4. So in the world of remainders modulo 4, 3 is its own inverse. Just like in the real numbers, -1 is its own inverse. -1 times -1 is 1. Similarly, 1 is its own inverse. 1 times 1 is 1. In the world of mod 4, 3 is its own inverse. If I were to do, in the same thing, if I try to do 3 plus 1, then this is 4 mod 4. I'm still in mod 4, and that is 0 mod 4 because the remainder is 0. So I'm seeing that 3 plus 1 is 0 mod 4. And so in the world of mod 4, 3 is actually -1 mod 4. So that is the additive inverse of 1 is 3. And the additive inverse of 3 is 1. And so it's a very mysterious world, and you can do this for every integer. So for example, if I do d is equal to 5 this time, then I'll see that 3 times 2 is 6 mod 5, which is 1 mod 5. So in mod 5, 3 is the inverse of 2, and 2 is the inverse of 3. Similarly, 3 plus 2 is 0 mod 5, and so -3 is 2 mod 5. So in mod 5, 2 is both the additive and multiplicative inverse of 3. So if you multiply 2 with 3, you get 1. If you add 2 with 3, you get 0. And that's different from mod 4. So in mod 4, we had the multiplicative inverse of 3 was 3. In mod 5, it's 2. Then the additive inverse of 3 was 1. And then here it is 2. So for every D, you get different set of rules. And using those rules, you can create very interesting mathematics. And in particular, we will see an application of this for crypto systems. You can create crypto systems using just modular arithmetic and nothing more.